Everybody, welcome on the next lecture on scientific and engineering programming. I hope that you can hear me. Can anybody confirm that, please?
Hello, yes, we can.
Thank you very much, Grzegorz, for this. Okay, so as you probably remember, last time I was showing you the part of slides where we were dealing with differential equations in Mathematica, and since I haven't had the computer with Mathematica, then I have shown you this only in PDF version. Almost everything could be shown in that way, but today I would like to return shortly to that subject to show you the animation. I hope they would run over the network. So let me share the screen. Okay, so you already should see the window with Mathematica, and let's scroll to the place which will be of our today's interest. You remember I was talking about the example of double pendulum, and I would like to show it again. I hope that at least some of you have worked with this example by themselves on your own. Okay, so as you remember, I hope you have an example with double pendulum, which is constructed of two rods, massless rods, at the end of which we have two masses, and everything is under the acting of gravitational forces. So we won't analyze maybe once more the form of the equation we construct here, because I have displayed very clearly what should we do. So we define the position for the first mass, for the second mass, then we define the system forces, there is gravity and also tensions. So these forces are derived from the third law of dynamics by Newton. And next, using the second law of motion by Newton, we will obtain the pendulum differential equations. So the differential equations which describe the behavior of the pendulum. So we write this equation for mass 1, for mass 2, and then we will get what you can see below. Okay, so this also shows the way I would recommend you to work with differential equations which are models of some systems, because usually we have some parameters for such systems. Usually we would like to run the simulation for different initial conditions, so it is quite useful to keep this data in separate variables. So you see, we have only the equations by themselves on a list set to a variable PD eqns, and now we will define p params, which will provide all the system parameters, also some external like gravity constant, and then we define the variable which is nothing else but the system initial conditions. So now we have these three elements with which we can work. So we will use NDSolve function. As I said to you earlier, usually the models of real systems are so complicated that they cannot be used, cannot be solved with DSolve function in a symbolic way. So we must solve it in numerical way. You know that there are some numerical methods which allow us to solve plenty kinds of different differential equations. So what I'm doing here, I'm setting together my equations, PD EQNS, my initial conditions, PEIC S, and then to these two elements I substitute parameters. which I have on a list. So I have to say to ndsolve function, what are the independent variable? As it was stated earlier, there are 4 of them, and the dependent variable is time. I have to give a range in which it will change. For these values, in this given range, Mathematica will find the solution. Since our equations here are not fully differential because there are some functions which have 0 differential order, Mathematica has noticed this and gives us a warning that these equations will be solved as a system of differential algebraic equations. This warning is given because sometimes by accident we forget to put some derivative somewhere, and then it is so that we think we are solving the differential equations, and actually they are mixed differential algebraic one. Okay, so you see that we obtain as a result the interpolating function for each of the variable of dependent variable. So what we can do next, we can just plot these values. So here I have plotted only 2 of them, θ1 and θ2, and velocity θ1 prime, θ2 prime. So you can see what is the time plot of that functions, but unfortunately it is quite difficult to analyze when you have some such different oscillations, how the system behaves. So we will continue with visualization of data by making of some animation. Of course, if you, for example, try to analyze some system which should stabilize, then time plot usually is enough to see that the value of the trajectory has stabilized at some point and the goal was achieved or not. But when you have such behavior, then it is hard to say what's going on in our system. Actually, this is the state, the internal state of our pendulum. So to visualize this, let's start with making some plots on which you will see what are the trajectory or the track on which move our masses in the system. So what I will do now, I will plot point P1 and P2. These points I have defined, these are the points at which our masses M1 and M2 are. And here, since the P1 and P2 also was defined in the parametrical way, that I have these parameters, in this case only the lengths, but anyhow, these are just parameters. So to visualize them, I have to substitute these parameters. Then I'm substituting obtained solution. As you remember, Mathematica, even if there is only the one solution, give it as a list of possible solutions. In this case, with one element. If there were more solutions, then they would be added to this list. Okay, so I'm substituting this solution, the first and the only one, and want to plot it in the time domain I have made the simulation. So you see that the first mass is moving on an arc, what is not quite surprising because it has to be arc. The only thing which the mass M1 can do is just rotation around the point where the pendulum is hanged. And when you look at the mass number 2, you see that the track is much more complicated because actually the mass number 2 moves with respect to the actual position of mass M1. Okay, so here for some visualization, I have plot also the forces with which masses acts to each other, so we can see, we can observe what are the values of them. But This is still not very readable because it is hard to say at which moment, where are we, and why these forces changes in that way. When we will make in a moment some animation, then it will be for us more readable. Okay, so let's try to do some plots which will be used for this animation, and we will model our pendulum as a line, just a line passing through 3 points. There is the beginning of the system, coordinate system where the pendulum is hanged. So we start with point 0, 0, and then we have to pass to point P1 and then to point P2. Apart from this line, it could be enough for the very beginning animation, but apart from this line, I have added 2 points of some diameter, one red and one blue, to show where exactly my masses are. Again, you have to substitute the solution you have obtained. You have to substitute parameters, since, as you remember, P1 and P2 are parameterized. Okay, so when you define this, let's do it. You can compute it at any time, which is the parameter here. And for example, at time t equals 0, I have such a line, and you can see that points are at these positions. So here is 1 almost 0, 1 minus 1. This is what I have set for the angles, defines such positions for the pendulum. Okay, so you can, of course, compute it at any point you wish, but it has to be in the time domain for which the solution was found. If you compute it for other values, like for example, you remember, or you can see that we have used the time domain from 0 to 15, and I wanted to compute what will be the pendulum position at time 20. Mathematica gives warnings that since this value 20 lies outside of the range of data in the interpolating function, it uses extrapolation. So it tries to extrapolate somehow these functions we have found and then returns the results. But usually for us, this is just rubbish. It doesn't make sense to make such extrapolation. As you have seen during the previous lectures, the problem is that when you try to plot such function with extended range, this warning doesn't occur. And it can be confusing because you think that you are watching something what is the result of your simulation, and in fact you are watching something what is the result of Mathematica extrapolation. Okay, anyhow, so now we are ready to animate our pendulum. So we make graphics of it. To keep the standard constant range of this plot, you have to specify this. Otherwise, Mathematica will recompute the plot range for every frame separately, and then it would look quite funny and you won't see what you really wanted. I'm setting here some axis ticks and some more smaller details. This is not very important. I would like to run it for time t from 0 to 15 with such a step. And here you can set the initial animation speed and also say if the animation should run just after computing this line. So here is the node. So animation has stopped on the first frame. And you see that for this specification, we have such situation that the first arm is placed horizontally, and the second arm is placed vertically. So now we can see how the pendulum will move. I don't know if it will be visible through your Zoom, but in fact, you are supposed to prepare such animations as well for the laboratories. So anyhow, you will do this in this case. Okay, so we can see that here there are some oscillations, in some sense not very much predictable. Okay. So we can add some additional elements to such an animation that, apart from plotting, animating the pendulum, we can plot the trace on which the masses move. So I'm applying the my parameters and my solution, which I have obtained. I'm applying it as a pure function to point P2. So I will show only the trace of the second mass. The first is not very interesting. And again, I'm defining this in the range for t changing from 0 to a given time t with a step which is specified here. It is chosen just by me, coming from experience. The larger this number will be, then the less frame you will obtain. And the smaller it will be, then there will be longer time to compute it. Okay, and now we will animate not only pendulum, but also trace. So we can use both these elements. And when we will do this, you will see that here is the additional red line, which simply shows how the second mass was moving. Okay, actually, in this system, there is no friction, and because of this, the system behaves quite chaotically. So this is, in fact, deterministic chaos, but if you start the pendulum from slightly different initial conditions, you will obtain totally different trajectory for this. So this is, let's say, the basic characteristic of deterministic chaos. But it is deterministic because you can determine it. You can say every time you will run the same simulation with the same initial conditions and parameters, you will obtain exactly the same chaotical line trajectory. Okay, so what we can add to our animation are forces, because it can be quite interesting to know how the forces act between the masses. So you have to put these forces in some scale. I have seen experimentally that dividing the forces by 100 will show them long enough, still visible and not too long. So now I'm defining arrow which comes to the point P1, and in the direction of that point with the length which is proportional to force F1. And of course I have to use this scale for the force. And I will put one red arrow to point to mass M1 and one blue arrow, as you can see, to point P2. Again, I'm substituting my solution and I'm substituting parameters, and this will be set as a function forces. So again, when I compute it at any point, you see I obtain two arrows, one coming from this point to this, and the second as defined below. So what I'm doing, I'm repeating what I have done previously. I'm just, apart from pendulum, apart from trace, I will plot also forces. So this is the only thing which has changed, but I have retyped that comment because I don't want to go back and forth in my slides because it can be a little bit confusing. And now you can see that there are these arrows which shows what exactly is going on. So you can see at any point you wish what are the forces which acts. Of course, these forces depends on the velocity of the movement of masses. So the faster the mass move, the force is larger, because these are centrifugal forces in our system. Okay, so this is more or less what you can do with such pendulum. You can try to start it from different initial positions. So maybe we will make one experiment with that. Let's say that we will let's say that we will set it at pi. So as you may know, pi and 0, this is equilibrium point for the double pendulum, but unstable one. Let's see what will happen. So we have to solve it. We can plot our time plots. So you can see that nothing interesting is going on. The pendulum is standing at this steady position because there is no disturbing force or any disturbing things which would cause to fall it down. Here you could see that there is some strange thing coming, but this is on the level of 10 to the power of minus 15. So this is just the computation noise, one could say. This is due to the accuracy the computation was performed. You see that Mathematica haven't shown whole this diagram, but something what in its let's say opinion is interesting. But of course you can change it by giving plot range to all. So you can see that this is a little bit higher. So we have 10 to the power of minus 14. Okay.
I'm sorry.
Yes.
Does Mathematica use like single precision, double precision, or arbitrary precision?
So for each such function, you can define what precision should be, and usually it is set automatically. And if no changes can be observed, then the precision is increased. But you can have the numbers of any precision here. So how to specify you can find in help. We won't discuss this here. Usually it is not necessary because this automatic mechanism which changes the precision works quite well. Okay, so let's make this small disturbance. So let's assume that the initial condition is not exactly at pi, but pi plus something quite small. I don't know, 10 to the power of minus 6. Let's see what will happen now. Okay, so now we can see that for some, let's say 3 seconds, it was almost in the steady state, but then it fell down and something started to change. Just see, for example, here we have such almost vertical line, which means that there was some rotation in the system because the angle has changed by more than 2 pi. So it has to start to revolute. But of course, the best thing is now just to see how it will behave. So let's animate pendulum trace and force. Okay, I have to change the plot range because not who. Okay, sorry. This is not what I wanted. I wanted to have to be it totally horizontal up. Okay, of course, we can see what will happen here. Okay, now you can see there is that rotation I was talking about. And again, the behavior of a system is quite chaotic, but I wanted to have both the arms pointed up. So let's change the initials. What I should do is, where is it? Okay, I have it here. So it should be pi, and this also should be pi. I want to do this so because in this state there is larger initial energy, which is here just the potential energy of the pendulum, and the behavior is much more interesting. So now you can see that there is much more rotation than it was previously. Okay, so let's try. So maybe we won't plot mass forces this time, only let's plot the trace and the pendulum itself. So I will change this plot range from -2 to 2. Okay, so we will be able to see the whole pendulum, and let's run it. So for some time it is standing up and then it is falling down. Okay, and you can see that it is rotating once to the left, once to the right, then it is standing up, then it is falling down, and it is behaving quite chaotically. And if somebody would say that real systems doesn't behave this way, so this is true, they don't behave, but there is one reason why, because there is a friction in these systems. But if you would like to try to build, let's say, frictionless or frictionless system, or the system with minimal friction, then you will observe such behavior. So to show you it, I try to run it through Zoom, but you can see it by yourself just by typing in the web browser in YouTube the high performance double pendulum, and you will find this video, which is showing how such a pendulum behaves. Okay, unfortunately, I don't know why it doesn't want to run. Maybe my computer is too busy at the moment. Okay, wait a moment, probably it will. But anyhow, just please spend 2 minutes and try to open a web browser, go to YouTube and type high performance double pendulum, and you will see what I'm trying to show you, but it won't want to work. Okay, so unfortunately my web browser has stuck, so maybe now, yeah, it runs, but I don't know if you get it properly on your screens. So you can see that it is rotating left, right, and here the operator has even give the initial velocity to the pendulum to give it more energy. Of course, you can see that the energy of the system drops and it moves slower and slower, but anyhow, the behavior is quite unpredictable. You cannot say when it will rotate to the left, to the right, how many times, and so on and so forth. So thanks to the friction, world is not so chaotic as it could be if there is no friction. Okay, so let me stop it. And we can now return to the slides in Mathematica. Where do I have it? Okay, so this is pretty nice. And as you remember, I was talking during the last lecture about the alternate approach, which is presented in the example on Wolfram page. So we take exactly the same double pendulum, but we model this a little bit differently because we will model this separately in the horizontal, along the horizontal axis and along the vertical axis. So we will write equations for the horizontal movement and for the vertical movement of each mass. So we will obtain more equations that they are, but to reflect the behavior of the pendulum, we are adding some constraints. Simply that the first and the second are mass has to move on a circle. The first around the beginning of the coordinate system where the pendulum is hanged, and the second around the first. Okay, and again we state the initial condition and so on and so forth. So you can see that we have obtained very similar behavior, but I won't present this now. We will see how much time we spent on other stuff with Mathematica, because there are still some issue I want to point you to them to show how to work with them and what is the, in my opinion, best way of utilizing them. But when you look at these two systems, you will see that you are obtaining different behaviors. And for such chaotic systems, it is quite crucial that because when you start with almost the same initial conditions, here it looks that you are starting exactly with the same initial conditions. After some time, you will obtain different results. Why? Because of the numerical errors which appear in the solution. So you have to remember that all the simulation you are performing in numerical way can have numerical error which can influence the system behavior. Of course, for stable systems, usually they won't be noticeable, but for such systems like this pendulum, they can influence the solution really much. Apart from this, there are some other phenomena which are hard to say errors in Mathematica or just its internal dynamics we cannot observe, but they causes that the system sometimes behave quite strange. So if we had time, I would show you this, but from this part, I would like you to remember that these are just the numeric simulation, so they can be influenced by the numerical errors and can not reflect the reality as they should. So this element should be analyzed. You should keep in mind that this can happen. Okay, so if we had time, we would, if there will be time, we will switch to this, and now I want to switch to the next lecture and say you a little bit about inputs and outputs in Mathematica, because it is quite crucial to know how to operate with them, and we haven't done much yet during this lecture on this topic. Okay. Wait a moment, where is it? I cannot find my palette. Why this? Wait a moment. I don't want this. But I want this. Give me a moment, please, because my windows are getting crazy. Don't know what's happening, in fact. I will try to share it again because it suddenly stopped. Okay, so I hope that you can see my screen now. And we have the slides for the next lecture, which consider the inputs and outputs in Mathematica. So in general, you have already probably this noticed, especially that this short introduction, which is given in the Wolfram Cloud, is displaying this, that everything in Mathematica which is taking part in a computation is either an input or the output, and that these elements are somehow grouped together. So when you have the output which is the result of some input you have provided, then they are grouped with these, let's say, brackets on the right. You can open these brackets, you can apply to them some additional elements. So this is up to you how you will organize your whole notebook. And also functions in Mathematica have an input. These are the arguments of the function, and have an output, which is a return value in general, which is returned by a function. Not always it is so that the function returns value, but quite often we have such situation. And here you have the example of such a function. Just to recall you, if you would like to build functions which behave more like procedures, then you can use module function, which allows you first of all define the local variables which can be initialized, and then specify the operations that should be done during the function computation. So this function can be understood as a mathematical function like sine, cosine, or something more complicated, but also can be regarded as a function like in any programming language. So I can have a sequence of some operations to be performed, some loops, some if statements, and so on and so forth. Okay, so anyhow. So this is another kind of input and output we have in Mathematica. We can go further, and as you see on this slide, Mathematica can read input from a file and save output to it. So this is also possible to interact with the external world. And this is, I think, not surprising because nowadays almost all systems, computer programs can do such stuff. So if you have, for example, a formula you would like to save to a file, you simply have to redirect it with this double arrow, which is composed with larger than sign, and then you have to specify the name of the file you would like to save it, and that's it. That's done. So here is the example. I have said it. There is a function file print. There are actually plenty different functions which allow you to operate on files and directories on your file system. And you see that this formula was put to this file. It is contained by this file. So opposite, if you would like to read in formula from a file, just use this input operator. And here I'm substituting this, what was written from a file, to my variable. So you can see that this is just a regular variable. For example, I can set the parameters values A and C, which occur here, to some specific value, like A to be B and C to be 2, and then you obtain this formula in the transformed form. So that's it. You can write this again to file. As a result, you remember, I hope, that %sign is used here in Mathematica to recall the last computation. You can use 2% signs to recall the last by 1, and so on and so forth. So this is what you can do. Basic input output on a file disks. Okay, before we will make something more, let's talk about this input which is given to function. I mean, let's talk about function arguments, because you have already seen that we are providing this in a special form, that after the name of the argument, there is this underscore, which has some meaning. And until now, I was saying that you simply have to do it and that's it. And now I will try to explain this meaning, because we will talk about patterns. So here there are some examples which show you how patterns work. So let's see, at the first line, we have here several functions: f of x plus y, f of x, y, two arguments, f of a, and finally f of 4. And here, in this expression, we would like to substitute this, what we are specifying here. So here I said that I would like to substitute f of a by a squared. And let's observe what has happened. The only thing which was changed is this f of a, because in such situation where you put a just argument with a name, Mathematica treats it literally. It means that there will be, if there will be such a expression which looks exactly like this one, function f and argument a, then it will be substituted by a squared. And as you can see, f of a has changed to a squared, and the other elements the other elements haven't been changed, so they have been left unchanged. Okay, so let's look to the second case where we have exactly the same expression, but now we are saying that we would like to change f of a, where a is something what will be called at this definition as a, to a square. So one could read that there is f which has an argument which we locally at this definition will call a, and we simply want to substitute a squared to see what will happen. And now you can see that not only f of a has changed to a squared, but also other cases, almost all of them in this case has been changed. So here we have f of x, so x is taken as this local variable a and is squared, so we have obtained x to the power of 2. Then there is the expression x plus y, so this expression was also taken as this pattern which appear here. So x plus y was named locally for a moment as an a, and it was squared, so we have obtained x plus y squared. This numerical value 4 was also assigned to this a, was squared, we have what we should. The only thing which has left unchanged is this f of x to y, because it doesn't fit to this pattern. There should be a single element which we will call a, but here there is no single elements in the function call, but there are two elements. So this f of x, y was unchanged. If I would say that here will be the second element, let's say y, then you can see that it has changed, and how. So the first element was taken and was squared, so we have this x squared here, what will appear. But if I say that there will be the second element c, so it won't change because there is no c literally. But if I say that it will be c underscore, so anything, any second element which we will mark as a c, then you will see that this x squared appeared here. Or maybe we can put that this will be a to the power of c, so you can see that there is x to the power of y. So you can specify exactly what will be the form of our elements. But you can also do something else. Let's return to this original example, that you will use the double underscore. And double underscore means any sequence of one or more expressions. So single underscore, this is a single expression, which will be referred, as you can see in this table, as you have named it. Of course, the name can be longer. This is just the regular name, like you applying to variables. And when you have this double underscore, what is called the blank sequence, it means that there can be a sequence of one or more expressions. There has to be at least one expression. So here we have the situation. I have applied this double underscore, and what you can observe is that now x and y are treated as a sequence, and they are consequently substituted to this a. So I have obtained x squared and I have obtained, wait a moment. No. X squared comes from this fx. So I have obtained this x to the power of y to the power of 2. Okay, so one more thing which I can add here, I can specify the type of this expression which is here. If you put just name and underscore, that will be an expression of any type. If you say, for example, that it has to be integer, then as you can see, Mathematica will apply this pattern only to these elements which have head of that type. So the element which is assigned has to be integer to do this. Okay, so maybe we should look at some more examples. And here, for example, we have a, b, c, and x to some powers. And I'm saying that I would like to change x to d. So the only thing which changed is this x. And now I'm saying that I would like to take any expression which I will call x, and I would like to change it to d. So you can see that Mathematica has treated this whole expression as a single expression and has replaced this by a d. And now I'm saying that I would like to have something which is to the power of 3 and would like to change it by d. So there is b to the power of 3 and x to the power of 3. So I have obtained 2d's. This is how it is. And now I'm saying that I would like to have something to the power of 3 and replace it with sign of x. So I have this sign of b and sign of x, where x is just this local name which appear here. Here you have two different ways of introducing just the same. You can use the superscripts or you can use this dash operator to get the power. And here is another example. I want to have something to some power, and I will call this something x, and I would like to replace it by d. So there are 4 such elements which fit to this pattern. So Mathematica is doing that is returning 4d. And finally, I would like to have something what I will call x to the power, to some power, which I will call y, and I would like to return d to the power of y. So you can see that I have obtained d to the power of 2, since there was a to the power of 2, 2 times d to the power of 3, since there was b to the power of 3 and x to the power of 3, and finally d to the power of 4, because of this c to the power of 4. And you have to remember that these rules and patterns work also on heads of the elements. So if I have such situation that I have some functions where the f, g, and h are heads of the expression, if you recall the internal representation of Mathematica, so I can say that I would like, in this formula, I would like to change f to k, or here I have to change sine to cosine, or here I would like to change list to f, then everything will be applied. So you'll see that instead of sine, we have cosine here. In this place, we have had a list of 3 elements. Now we have a function with 3 arguments, and here I have changed the head list to plus. So these elements of this list was sum up, what is very similar to this what I will do when I use the apply function. As I have shown you already that this double @ sign is used as a synonym to the apply function, so you can type it in that way. Okay, so if you would like to extend these patterns, I won't go into details in these topics. Want to show you some possibilities was, let's see, I can have the alternate patterns. I can say that A or B should be changed to D, or I can say that A, one or more A should be changed to D. Any number of A's which will appear here then will be changed to D. So as you can see that I can just provide the patterns. Here I would like to divide this list in two elements, but there will be a sequence which I will call X and a sequence which I will call Y, and I would like to get X and Y. What Mathematica do? Mathematica is trying to take as a first sequence the shortest possible sequence. So you can see that the answer is that A is put alone as an element of one element list, and the rest, let's say the tail, is put to the second list. But actually, this pattern, which is given here, can fit this list in several ways. So I can have, for example, AB and then CDFG, or I can have ABC on the first list and so on and so forth. I can change the behavior of Mathematica by providing some quantifiers which would say what should be the property of the element. So for example, here I'm saying that this first element should be the longest one, the longest possible, and Mathematica has taken almost all elements apart from the last one to the first list. Then I would like to have this longest, actually this is the default case. Or I would like to have this shortest, I can do it. So let's look at some examples. We have to find the longest sequence of integers in the list which consists of integers and non-integers. You can see that there are some symbols somewhere in between. So you can solve this task in this way, that you are saying that there will be something at the beginning and there will be something at the end and there will be something in between which is integer, and it should be the longest one. So you can see that Mathematica has returned this in that way. If you don't specify that it has to be the longest, so Mathematica will return the first found, and here the first found is just the 3, and by default it is the shortest. And maybe you have noticed that here I have put something new. There are no 2 underscores, but 3 in a row. 3 underscores, this is blank null sequence, which is any sequence of 0 or more expressions. If you have 2 underscores, there has to be at least one expression. So this is the sequence of 1 or more expressions. 3 underscores, this is the sequence of 0 or more expressions. Okay, so I propose we will make a short 3-minute break so you can look through the window, take some coffee or just short walk, and then we will continue. Thank you very much. Okay, so we can return to our slides. Let me share the screen. Okay, so knowing all what I have said about patterns, now we can define the functions in the way that we would understand what the elements of the definition are. Okay, so the general rule during the defining the functions is that you should use patterns to introduce the arguments. So simple example, you already know this. We have function with a single argument, f of something, an expression which we call locally x, and function is just to square the x. So you will see f of 4, 16, f of a squared, f of x squared, f of x plus b squared, f of two argument xb not computed because it doesn't fit to this pattern, and finally f of a list x plus b, a, and 4, the elements of the list squared. Why? Because this list is a single expression and it was passed to this function, and it do the following, that it powers the list, and since the function of power is listable, then this power is applied to every element on a list. So you have x plus b, a, and 4 squared here. So just remember that this function f works on a list because the power function is listable, not because our function is listable. By default, functions defined by user are not listable. So the only thing which is going here, this list is treated as a whole, a single expression by our function f, and is passed to function power, which is listable. Here you can see the short description of the power. Just to recall, if you would like to get some help in Mathematica, simply write a single or double question mark and then the name of the function you would like to learn about. So single will give you only the short description of the function, and longer will also describe some attributes and additional elements if there are some configuration. Okay, so you can see that, for example, power has a default value defound. Okay, so let's do the next. Let's say that f of a, see that a, this is just a literal, an element which has to be taken literally, and we say that f of a should be Alice and f of 4 should be 44. So now when you will ask what is f of 4, you won't obtain 16 anymore, but you will obtain 44. If you ask what is f of 4, you will obtain Alice. What is Alice? Just a symbolic value. You see, it is printed in blue. In my Mathematica interface, it means that this is not defined. Okay, actually my function is also not defined in this printed in blue because I haven't computed this line. But if I will compute it, you will see that the f will turn to black. But Alice will stay blue since it's not defined. And look, for example, f of 4 is 44, but if you call f with this list and there will be 4 or a, then they simply will be squared. Why? Because, I repeat this once more, this whole list is passed as a single expression to function power, and function power simply compute the squares of elements of this list, and that's it. So don't be surprised in such situation when you would like to have some special cases, they won't work if the special cases are put on the list. Let's look closer to our function f, how it is. It is said that there is a global function f which has 3 elements of the definition. We always start with this more specific computed at some point or at some ranges, and then we go to the more general definitions. So it is said that f of 4 is 44, f of a is Alice, and f of something what we will call x is x squared. Of course, this formula, this rule, this definition will be applied if these two first one are not fulfilled. Okay, so we will add something more to our definition. We will say that we would like to have such the definition that f of something what is called x under the condition that x is smaller than 0 will be minus x. So for all negative numbers, we would like to give the positives. So what is f of minus 4? Now it is of course 4. Let's look at our definition. It's getting quite complicated. So now first we have these two special cases at the specific value of 4, at the specific value of a, symbolic, but this is just a one value. Then we have this what is on a range. So if if x is negative, this definition will be applied. And finally, we have this general, which will be applied for all positives, but not for 4 and a. This is how it looks. Okay, so we can do another thing, what I have shown, but now let's look at this a little bit more. We can specify the type of the argument. So let's say that now we are defining the function g, which we will say that it will have an argument, an expression which we will call x, and this expression has to be an integer, and then it will be squared. So you see that this function works only on integers. So g of 4 is 16, but if you have g with a list with 3 elements, and among them there is an integer, it won't be squared because it doesn't fit. This element has a header list, not an integer. Okay, so another example, we will define. Yes?
If we would make G listable, it would work?
Yes, then yes.
Okay.
I hope that I have such an example here, and it should be nice to have it. But simply you have to change the attribute and then it will be listable. So this is quite important thing because sometimes you can be surprised why things work different than you think they should. So this is why I'm putting so much attention to this, because not many languages have such apparatus to interpret the arguments. Okay, so here we say that G will have a single element, single expression as an argument, which has to be symbol. And now you can see that G of A is computed, G of X is computed, but G of X plus B, this is just the expression, not the symbol. So it's not computed. And again, this is just the list. Okay, so you can define, of course, functions with several arguments. And here we have the example where there are 2 arguments, the first x and the second y, but you have remember that this is just a pattern. So Mathematica will compute it as a pattern. This is what I have shown 2 slides ago, that something may be longer, something may be shorter. Just remember, Of course, if you provide exactly 2 arguments to such a function, there will be no problem with distribution, the distribution of values to these elements. But just remember that actually, so this is not like arguments in ordinary programming, in any other languages programming, but this is pattern, and Mathematica just try to fit patterns. Okay, so now I'm saying that it will be x squared plus y squared, but there is some special case. First arguments any, and second y, and this is our special case. So you can see that when you specify something which will have y at the second position, then you will obtain this special case, which is here. Okay, so as you can see, we have defined function f previously with a single argument, now with several arguments. So our definition of f is quite long now. So here you have this part from the single argument case, and here you have this part of 2 arguments. But in general, you can say that your function, let's take another function h, will have an expression which is not a the function will have an argument which is not a single expression by a sequence of some expressions. And now you can see how it is squared. Again, we will square it, that when you have this this is the most interesting, I think. So when you have this x plus b, a, and 5, not last, but last by 1, x and b, you have here 2 arguments, and this is taken as a sequence of arguments. So you have x to the power of b, and then it is squared. Okay. So let's observe some arguments behavior on these simple examples, which I hope will show you another kind of differences between this, what you can do in Mathematica, and this, what you get in programming languages like C, C++, or Python. For example, when you have variable var and you assign to it value 3, then that's okay. But and when you try to add something to it, like 7, you will obtain 10, and variable var will have value 10. But if you do the same with an initialized variable, and you will say that var will be this variable plus 7, then you see that the recursion occurs, because Mathematica is seeing the following, that as a var1, it has to take a var1 plus 7, and var1 is defined as a var1 plus 7. And it would run in this recursion forever, but since this error, when you are not experienced, especially when you are not experienced programmer in the Mathematica, occurs quite often, then there is a special value, recursion limit, which simply say what is the max depth of recursion. And as you can see, it is set to 1024 in this case. So if there will be some computation which will need recursion of larger depth, and you know that this is the computation intended to be performed, so you have to increase this recursion limit parameter. You can learn more about this, of course, going to help and look like it.
I'm sorry.
Yes?
So if I understood it correctly, it first like creates how how variable is defined, and then to display it, it tries to calculate and goes into recursion.
Yes, exactly. Because this what you define, this is just a rule. which Mathematica is trying to apply. And now Mathematica knows such a, or maybe not rule, this is wrong word, this is a kind of relation. Mathematica now knows that var1, this is nothing else but var1 plus 7. And since it knows that this is var1, that this is plus 7, so tries to use recursion. But usually in your programs, this case doesn't occur because usually you will try to initialize your variables somehow. But if you would forget to initialize variable, you will get totally different behavior than in sequential or objective languages, which maybe you are familiar with. Okay, so what Mathematica has returned our expression as an argument or hold function. And hold function, this is the function which prohibits from computing. So simply keep this expression not evaluated. So sometimes it is so that you are constructing functions and you would like to compute some elements of these functions on a specific level of computation, not at the very beginning, for example. So you can use this hold function, but in fact, this is a very rare case when you are using this function. Okay, so let's see what are the consequences of such the behavior. Here we have defined the prots function, which has a single expression argument, which we will call x, and it consists of sequence of 3 operations. First, we have to substitute square root of x to variable zm. Look, this will be a global variable here because we are grouping with the parentheses. If we would like to have it as a local one, we would have to use the module function. Then we want to set x as this variable plus 3, and then just return x. So it looks like nothing wrong is going here because just regular computation with some global variables set square root to zm, then to this what you have obtained, add 3 and set it to x, but you can see that it very rarely works. For example, when you call the function with some variable u, then you have obtained the recursion depth because of this situation that the x appears, which is u, appears here in 2 definitions on both sides, so the recursion occurs. When you, for example, think that you could compute this function for a numerical variable, then you see that you won't do this because there is substitution to this what is called x, and since this is a numerical value, so you cannot assign any value to row object 5. Again, when you define your variable yi equal to 7 and try to call your procedure, your function with this variable, again, you won't obtain the result since yi have a value of 7. This value of 7 is provided here and is interpreted as x, and you cannot substitute to a numerical value anything. So again, it won't work. So at the first sight, it looks like a proper function, but you see this is not a function which you are able to use. When you have such a case, to obtain the function which will do what you want, you have to use local variables. So we have here the local x and local zm, and now we are substituting this value to this local zm. Then we use the local x, which is just a x symbol, and then we return that local x we have computed. Now, when you compute this function with a symbol, you will obtain the result. If you compute this function with a numerical value, you will obtain the result as well. So just remember that arguments in Mathematica behaves in this way, because actually these are not variables, but these are patterns. So this is just a pattern which will be compared with the expression given as the argument, and then the proper action will be undertaken. Okay, we have some more possibilities defining arguments in Mathematica, because, for example, first is that we can have default values for arguments. So in this case, the argument becomes an option. So if you don't provide these arguments, then they will take the default values 1 and 2. So for example, J of ABC, this is JP of ABC, it was substituted. But if I skip the last argument, then 2, the default value will be taken. Again, when I have only the one argument, the second and the third will be taken as a default value. So you can divide this with column, and of course you can combine this what we have learned yet, that we also use the head of the expression and the default value of that expression. And there is also a special operator, a dot, and then the expression will be, if omitted, will be given a built-in default value. So for addition, the default value is 0. For multiplication, the default value is 1. And for power function, the default value is also 1. Okay, so here you can see how it works. Here we have omitted this second element with default value, since there is the addition, then the element which is the default is 0, as this table says. Okay, so here we have the simple formula, which is a function which returns coefficients of a linear function. So I was saying that there will be something maybe with default value plus something multiplied by x, and the second argument will specify what is the variable of our linear function. So you can see that if we have the equation ax plus b, then b and a are returned as we expected. When we have 17x plus 4, then 4 and 17 is returned. But when we skipped the this free element 4, then 0 is returned. And if we have the x alone, then 1 is returned, because this is the default value for multiplication which we have here, b times x. This is this multiplication. Okay. What we can do, I won't describe this, and I won't explain probably in this what you would do. It won't be a lot of occasion to use this mechanism, but you can have functions with variable number of arguments. And just remember, this what you specify here is a pattern. And then when you call Mathematica with some sequences, Mathematica tries to fit that pattern according to their rule, and then it's returning what it is here. Okay, so just remember that this how it works, but maybe somewhere in the future you will use. Okay, and finally we can get to this part. We have had some minutes ago a question about that your function can be done as a listable function. Okay, so let's return to this example we already have. So we have this function f, which has this long definition. And again, we call it at a special value f of a, which was Alice, f of 4, which was 44, and f of least, where 4 was turned to 16, because this whole list was passed to that function, which is the definition of our function, x squared. And function power is listable. So this is why it was applied. Okay, so let's see what are the attributes of our function f. At the moment, there are no attributes, so we will set one. We will say that our function f is listable. So of course, now attributes say that this function is listable. And look that the behavior of our function has changed, because now this function, when passing to it a list, wraps itself, applies itself to every element of this list. So we will have f of x plus b, f of a, f of 4. And then the definition is applied. Now there is no the case where the list is passed as a whole to power function. So now you can see that there is this Alice and 44. So changing attribute of a function changes its behavior magnificently. So you can observe this here. Okay, so we can of course clear attributes and clear all. So here you have the set of these functions which are useful while working with your own functions. So this behavior being listable is quite useful, and you can do a lot of things without any loops. And if there will be no this idea of being listable, then you would have to make loops to repeat computation. So just please utilize this. And for example, when you look at these attributes of plus function, so you see that it is listable, but it is also flat numeric function, one identity, orderless, and protected. Protected means that you cannot change its definition, but since you are able to change attributes of functions, so you can unprotect the plus function, then say that there is a special case that plus with 2 arguments, 2 and 2 is equal to 5. And from that time, every time when you will write in Mathematica 2 plus 2, you will obtain 5, with full consequences of this fact to the algebra, which you have just destroyed by such definition. Okay, since the next slide treats about the external data operation, we have finished about functions, so I think that this is a good moment to finish our lecture. Actually, we run out of time, and if there is any question you would like to ask, so please ask. I try to answer, and if no, we will see on Friday at the laboratories, virtual one, of course. Okay, so do you have questions about these topics? So if not, so I will give one more comment. You can see that this lecture is constructed in such a way that at the very beginning we were quite in a hurry to get some basic idea and to start working with Mathematica in a special case. So I've got to this simulation system of double pendulum quite fast, without explaining all the details what we are doing, and actually the exercises you are performing are prepared so that you have some layouts of them and you have only to fill some missing parts. And to fill them usually is quite easy because the examples how to fill them you can find in that lectures. And now we switch to this part where when I try to explain you some behavior of Mathematica, which in my opinion are quite important because they are different from the behavior of many other languages. For this who already has learned some other languages and which extend the abilities of Mathematica much. So you can simply use them in very clever way usually. Okay, so thank you very much for this meeting and we will see probably on Friday. See you then.